The first video on circular motion looked at radians and angular displacement and centripetal force and one or two examples. So this second video will look at lots more examples of circular motion, all of which you need to be really confident with in terms of explaining and also with calculations as well. So the first one is this type of bridge, a humpback bridge. So obviously slightly exaggerated here. Really typical question. So first of all, we'll consider if the car is just parked on a bridge like this, then what are the forces? Well, we've got the weight acting downwards, we've got the reaction force acting upwards, and if it's not moving, then these forces will be balanced, and we have zero resultant force, so that's straightforward. So if we have car moving at a relatively slow speed, then the weight downwards is still the same, that hasn't changed. But now, importantly, the reaction force acting upwards has reduced a little bit. Now it must reduce because we only have these two forces. So the combination of these two forces must provide a resultant force towards the center. We give a name to that as centripetal force. So the reaction force is slightly smaller. So now the resultant force is the combination of these two. mg take away the reaction force. So it's part of the weight which is providing a centripetal force downwards, and that must be there because the car is following a circular path, moving in a circle. So it has to be part of the weight, or the weight take away the reaction force, which is providing the centripetal force. So very often we look at a scenario when the car is moving very quickly. It's moving so quickly that the wheels are on the point of losing contact with the road. So now the reaction force has reduced to zero. So it's the entirety of the weight which is providing the resultant force. So the resultant force is equal to the weight. We could also say the centripetal acceleration is equal to g, because g is the acceleration due to gravity. So this is the maximum centripetal force that this situation could provide, that this car could provide. So we could calculate the maximum speed the car is traveling at before the wheels start to lose contact with the road. And this would be the example calculation of that. So we've got a scenario here. So the earlier parts of the question might ask you to calculate the weight, maybe the reaction force when it's stationary, which would just be equal to zero. So here we go. We've got what is the largest speed the car can travel before the wheels lose contact with the road. So let's just put into contact what we've just talked about. So the point at which the wheels lose contact with the road, the reaction force has reduced to zero. So the weight provides the centripetal force. So this becomes relatively straightforward. So Fc, the centripetal force, is equal to the weight. So mg is equal to mv squared over r. So that's relatively straightforward. In fact, even though we were given the mass of 1,200, the mass is the same on both sides of the formula. So we could calculate with the mass, but the mass is going to cancel anyway. So v is equal to root gr if we rearrange this expression here. So we've got 9.81 multiplied by the radius we're given. Square root is equal to 14, so our answer is 14. So the maximum speed is actually independent of the mass of the car. It only depends on g, which we assume is fixed on the surface of Earth, and therefore the only variable really is the radius of the road. So what sounds like quite a complex question actually simplifies to a relatively straightforward calculation. Let's have a look at the second example. So a conical pendulum. I would recommend you do a Google search or YouTube search to see what this looks like if your teacher has not shown this to you anyway. Because it's a really typical thing in the exam. It links to different types of fairground rides and so on. So we've got this straight rod in the middle, we've got a bit of string and then a mass, an object at the end of the string, and this thing is rotating in a horizontal circle. So we've got a length of the string, we will know the mass of the object, and then the radius is this value here. And very often we talk about theta measured from the vertical. So we could analyze this and think, okay, well the tension is doing two things. If I split the tension into two components, so its horizontal component and its vertical component, then in terms of theta, theta here or up at the top, then t cos theta is going to be this component here, and t sine theta is the horizontal component. So what are these components doing? These are quite important. So the horizontal component of tension is acting towards the center. This is the thing that provides the centripetal force. But the vertical component, the adjacent T cos theta, is also doing an important job. That is balancing the weight mg. So we've got two statements here. Let's just go through that again. So this is moving in a horizontal circle. If it's moving in a circle, it must have a centripetal force. So that's provided by the horizontal component of tension, T sine theta. If it's a horizontal circle, it's not moving up or down, then the weight downwards must be balanced by a force upwards, the vertical component of the tension, T cos theta. So we could calculate, if we know the weight, we could calculate T cos theta. If we know the M, the V and the R, we can find the mv squared over r, we can find the horizontal component, and then we can find the angle theta, which is typical example given here. So we've got an object, we know the mass, we know the radius, we know the speed. First of all, find the centripetal force, and then it says find the angle between the wire and the vertical. So that this is a really typical question. So part A is pretty straightforward. mv squared over r, nothing difficult about that. Make sure that we convert centimeters into meters, and we get 3.85. Okay, that's straightforward. Then we need to apply what we've just considered in the previous screen. So vertically, the forces are balanced. The vertical component of tension is balancing mg. I know the mass and I know g, so I can find the vertical component. We said that the centripetal force is provided by the horizontal component of tension. So if I know these two components, then I can do a little bit of trigonometry. The 1.96 is the vertical component, the 3.85 is the horizontal component. I'm trying to find theta, so tan to the minus 1 of 3.85 over 1.96 will give me 63. So this part B is the tricky bit, and this is really, really important. There'll be lots of different scenarios which use a very, very similar approach. So let's have a look at some more examples. Right, we have a car cornering on a banked road. So this could be a normal car with a very slight camber. So most roads, if you have a corner, there'll be a very, very slight angle of elevation, maybe just a few degrees to help the process. But we can see on a racetrack, so famously this is Daytona racetrack, we have a very extreme banked surface here, maybe 30 or 40 degrees. And in fact, if you go at the right speed, you can point your wheels straight and still move in a circle. So normally we're turning the steering wheel, which turns the wheels, but actually, and in fact, this effect here that we'll talk about will help you move in a circle. But actually, if you're going at the right speed, you don't need to turn the wheels. You can just go straight into a curve, and the banking effect, as we'll see, will help you move in a circle. So what is going on here? So this is viewed from the front. We've got the car or the object here. We have the weight always acting downwards. We've got the angle of elevation theta. Alternate angles, this would be theta here. 90 degrees, 90 degrees, this would be theta here. So the angle between the reaction force and the vertical is theta. So it's all about the reaction force here. So important point, we've seen this earlier on in the course in mechanics. So if we have a horizontal surface, then the normal reaction force is vertical. But if we have a slope at a particular elevation, theta, then by definition, the normal force must be at 90 degrees. So don't make the mistake of drawing the reaction force vertically. That's totally wrong. So I can consider the components of the reaction force. If I split this into its two components, so this is theta here. So T cos theta is the vertical component of the reaction force. T sine theta is the horizontal component of the reaction force. So this is actually almost identical mathematically to the previous example. So the part of this system that is providing a force towards the center of the circle over here is the horizontal component of the reaction force. So the centripetal force is provided by T sine theta. That should be R sine theta. Let's change that. There we go. R sine theta. Marvelous. So it's the reaction force sine theta, the horizontal component of the reaction force. But the vertical component is also doing an important job, as we saw previously. That is balancing the weight. So the weight is balanced by the vertical component of the reaction force r cos theta. So the calculations are going to be very, very similar to the ones on the previous screen with the conical pendulum. Because if we know the weight, then I can work out the r cos theta, the vertical component. If I know m, v and r, I can find the centripetal force, which will be my r sine theta, and then I can work out theta, the angle from the vertical. So very, very similar calculations. One final example, again, almost identical. I need to change that T to L, I think. So this would be planes banking. So this is one of the main ways that that planes will turn a corner. So they have the flaps, the ailerons on the wings, they go up or down. And you'll have experienced this if you've been in a plane, and you might have an extreme bank if you've got an extreme turn. So we have the air flowing over the wings, which generates the lift. Similarly to the tension, similar to the normal force, this is at 90 degrees in this case to the wings of the plane. So again, we can split this into its components. I have a vertical component of the lift force, I have a horizontal component of the lift force, and I can work out these values in terms of L and theta. So L cos theta is the vertical component, L sine theta is the horizontal component. And once again, so you can see the similarity here with the previous two examples, the reason we move in a circle towards the center on the right of the screen is because we have a centripetal force that is provided by the horizontal component of the lift force, L sine theta. And then the reason we're moving in a horizontal circle and not going up or down is the weight downwards is balanced by the vertical component upwards of the lift force, which is L cos theta. So again, if we know the weight, we can find L cos theta, they will be balanced. And if I know m, v and r, I can find the centripetal force, which is L sine theta, and we can work out theta. You might also get questions similar to what would happen if the lift force was constant, at constant speed, constant thrust, and a plane goes into a banked turn. Well, we can see that if the lift is now no longer vertical, then L cos theta will be lower than L. So that will result in the weight being greater. So the plane will start to lose altitude if we turn it into a banked corner. So you may even notice this when a plane goes into a banked corner and wants to maintain altitude, then the thrust needs to increase to generate a larger lift so that the vertical component still balances the weight.